Okay, today I want to talk about the common emitter amplifier. And I know it looks kind of complicated at first glance, but it's really not that bad once you look at it a little bit here. Drag it back over to the side a little. Last time we built a voltage divider bias, and that's mostly what I have here. I really haven't added that much to that voltage divider bias circuit. I'm going to drag it out here so you can compare them. And that's the circuit we looked at last time. I even used the same values for everything. The only things I added are the 3 capacitors, the load resistor over here on the far right. I added that. I added the capacitor there, and the one down here, and then the AC supply. Now, what an amplifier does is we input an AC, a small, this is just a millivolt, a small AC voltage into the base of the transistor, and it excites the transistor to the point that it carves out from this DC supply a bigger version of that AC. So we draw that, and we got a small AC going in, and hopefully we'll have a great big AC coming out. Now, there's limits to that. I mean, I can't go over that 15 volts. In fact, I've got to be, remember we got to bias and have our operating point or quiescent point up in the middle of that 15 volts. So we could probably go +7 to -7 as an output with this particular setup. Now we can do an AC equivalent circuit of this and a DC equivalent circuit. When I want to do the DC equivalent circuit, I short circuit all AC supplies, but I open circuit all capacitors. When I open circuit C1 and C2, well, that really chops off the AC supply and the load resistor when I open circuit those 2 capacitors. And when I open circuit C3, well, it don't chop anything else off, but it opens up itself, so it's like it just disappears for the DC. So I end up with exactly the same circuit we had last time. Now I'm just doing that on paper. I don't do that in real life because we want to. We've got both AC and DC in the circuit, and we want to be able to do both an AC and a DC analysis. So we learned last time how to do the DC part. Gave you a step-by-step procedure. Now, we can also do an AC analysis, though, because what we eventually want to find is the gain. How much bigger can we make that output signal be than the input signal? We call that the gain of the amplifier. Now, some books use the letter G for gain. Most of them, including this one, use the letter A. I think they actually put a little V subscript on it to show that it is a voltage gain, because you can get into power gains too. We're not going to get into that in this class, but you can get into situations where we want to talk about how much power is amplified or multiplied. Now, what we ultimately want to find is be able to find that gain. So if I know what my input, that should be a VN instead of a V2 there. I want my output voltage out here, my AC output. We call that V out. We want V out to be that gain times the VN. All right. Now, if I set this amplifier up in a laboratory, or if I do it on multisim, I can measure V out and I can measure V in, and I can define the gain in terms of those voltages. And just divide both sides by Vn. So I can measure that gain that way, measure V out and Vn, divide them together. But I also want to be able to calculate what that gain is going to be based on the transistor and the resistors that I have in the circuit. So let's look at how we can do that. First, we need to find the AC equivalent. Now, the one we got over here on the right is the DC equivalent. But now I want to find the AC equivalent circuit of this amplifier. Now, for AC, we have chosen the capacitors so that they are short circuits for AC at this frequency. We're at 5 kilohertz. You can calculate it out, find the reactance just like we did earlier in the semester for capacitive reactance. It comes out to be something like 0.026 ohms. So that's essentially a short circuit for AC. Now, C1 and C2 we call coupling capacitors, because again, their whole job is to couple different circuits together, block the DC from other circuits into getting into this circuit, and block the DC from this circuit from getting into the other circuits, all the while letting the AC pass right on through. So C1 and C2 do that job, and we call them coupling capacitors. C3 we call a bypass capacitor. We want RE in the circuit for DC, but for AC we want that emitter shorted directly to ground. So C3 is bypassing the emitter resistor for AC. So to do my AC circuit, and also let's talk about VCC for a minute, there's supply voltage up here. For AC, that acts like a short circuit. And since it's tied to ground, both R1 and RC are grounded at the top. C2 is like a short circuit. Let me go ahead and go to the next drawing. Let's open a new page and let's see. AC. Here we go. AC model, I call it, but it's the AC equivalent circuit. And let's go ahead and put that original circuit back up there beside it for a minute. All right, C1 got shorted out. Remember, all my caps get shorted and my VCC supply gets shorted. So VCC got shorted, that means RC goes to ground now. RC goes to ground. R1 also goes to ground. So R1 and R2 are now in parallel with each other and in parallel with the AC supply. RE was bypassed by C3, so it's gone completely. And then RC and RL are in parallel. C2 is shorted, VCC is shorted to ground, so I can turn the RC down and it's right beside the RL. Now, I'm not going to worry about R1 and R2 for the moment. I want to talk a little more about the right-hand side of the circuit. There is an internal resistance to the transistor, to the emitter portion of the resistor for AC only. And we use lowercase letters for some of the R's that we're going to deal with here that are just for AC only. We call this one little RE prime. That is a resistance that's internal to the base emitter circuit or junction of the transistor. And it is typically going to be equal to 25 millivolts divided by the DC emitter current that we found from the DC equivalent circuit. We saw how to do that last time. Let me see. Here's the steps we went through last time. So we found the emitter voltage. We found the base voltage first from the voltage divider, subtracted off 0.7 of a volt for VBE. That gave us emitter voltage, and then we just divide that by RE, and that gave us the emitter current. So if we did that DC emitter current, so we can divide that into the 25 millivolts, and that gives us, I need to do that. Anyway, that gives us what we call a little RE prime. Now, we can also Since RC and RL are now in parallel with each other, we can find little RL just by doing those two things in parallel. Like that. And then we're going to find that the gain of the amplifier is just simply this little RL over little RE prime. So let's go through and calculate some of those things. Let's see. I don't know if I have the DC emitter current handy. We'll have to calculate that real quick. That'll be 2.2 minus 0.7 gives me 1.5. Let me start a new page here. All my components out where we can see everything. All right, if you go through the voltage divider, R1 and R2, remember the voltage divider formula was, and this is going to be VB, it's going to be the supply voltage, 15 volts, times the bottom resistor over both resistors added together, and that's 25.6. And there's a K there I left out. 5.6K plus 4.4K. And if you calculate all that out, that's going to give you 2.2 volts, but that's VB. Now, that's more than enough voltage to forward bias the base emitter junction, so we know VBE is 0.7. So VE is going to be VB minus VBE. It's supposed to be a B. Or 2.2 minus 0.7, 1.5 volts. And we got 1.5 K on for RE. So IE is going to be VE over RE, 1.5 volts over 1.5 K ohms, or 1 milliamp. So now my little RE prime now this one's just a constant, just like the 7/10 of a volt. I always use it. Some books use a little bit different value, like some books will use 0.65 or 0.8 or 0.75 for that VBE, and some of them will use different, slightly different values for this 25 millivolts. But our book uses 25 millivolts, and that's what I've always used, and it works out fine. 25 millivolts over 1 milliamp, or 25 ohms. And we also need the little RL, so that's the big RL in parallel with the big RC. I don't really have room to do that here, so let's go to the next page. RC was 6K, RL was 5K. So that's going to be 30K squared over 11K, or 30K over 11. A little under 1K. Yeah, I get we call it 2.73K. So now my voltage gain is that little RL over the little RE prime, 2.73K divided by the little RE prime was 25 in this case. So when I divide that out, I get a gain of 109. All right, so I don't have room to pull the picture back up, but if you can remember from the schematic I had earlier, I had an input voltage of 1 volt RMS. So you could use this on either peak or RMS, either one. If you use RMS, the answer comes out in RMS. If you use peak, the answer will come out in peak. It works either way. So my output voltage for this amp, excuse me, is 109 times that 1 millivolt will give me 109 millivolts. So we've multiplied that voltage waveform over 100 times. And we could do more. We can stick another amplifier just like this one at the output of this one. Stack them up, so to speak. Have the output of one feed the input of the next one. We call that cascading. And so we can make bigger and bigger gains. We just have to watch our voltage limits, whatever voltage supply we're using. We can't ever put out more than that, and really about half that. Because again, our operating point needs to be about halfway in the middle of the load line, so we've got room for the voltage to swing back and forth either direction. I do want to look at a variation of the common emitter. One problem that we can run into with the common emitter is it's not very stable as far as temperature and aging. So we can make something here we call a swamped common emitter. And the only difference is I split the emitter resistor. I kept out 100 ohms right here. It's still 1.5K if you added those two together. And I only bypassed the bottom part of it. Everything else is the same. This will cut down on your gain, which you really want your gain to be bigger, but it will make the gain stay more stable over time and temperature than just a straight common emitter amplifier. And the gain for this one, everything else being the same, is going to be that little RL over little RE prime plus this extra bit of resistor we have there. So in this case, instead of 109, we wouldn't have them, but probably picked too big a one for that. We probably should have made something more like 20. And that would give us a gain, maybe a 5, and then we can have two of them together. Making a gain of 100, it's going to be just a little bit, it's going to have a gain just a little bit more than one, which is okay sometimes, but typically we want more gain than that. So this would be divided by 125 now, the 27.27 divided by 125. Giving me a gain of 23. Not as good as 100. That was the same numbers we had before. Except now we have this extra 100 ohms down here. And that gives me a gain of about 23 now instead of 21.8. So I guess we call that 22. Which that is, that's not an atypical gain for an amplifier. Sometimes that's good. Another problem that we can run into is what happens if this resistance gets small. Remember, that resistance feeds into the gain formula. It goes in parallel with the collector resistor to make that little RL. So if this number is small, that's going to drive our gain way down. So I'll show you one more trick that we can play to get that resistance up, so to speak. Let's start a new page. We'll use something we call an emitter follower. Here it is. At first glance, you may think it looks a lot like the one we were just looking at, and it does look similar, but the two things you need to notice right off is, number one, there's no collector resistor. And instead of pulling the output from the collector, we're pulling it from the emitter. Get my pointer again. See, here's my output coming out. And notice I'm using a much smaller load here. Now, for this one, we can calculate a little RE, or you can call it RL if you want to, by taking the load and the emitter resistor in parallel. I don't remember which one they call it in the book, since they were using little RL in the common emitter, or common emitter circuit. We'll go ahead and use little RL for this. And that's RE. And again, the capacitor for AC, remember the capacitor is going to be short, so those two are in parallel. And the collector shorts directly to ground. Remember, in AC, the VCC acts like a short circuit. So that's why we also sometimes call this common collector. When they say common emitter and common collector, they're using the word common to refer to ground. Common is just another word for ground. Anyway, RL is going to be RE times big RL. Now notice I haven't changed my base bias circuit or my emitter resistor. Well, I guess I did change the emitter resistor. I meant to leave it the same too. Let's make it the same for this argument as it was in the other one. I meant to leave it the same. It was 1.5K. So it's still going to give me the same emitter current and the same little RE prime. So I'm going to write that over here. We already found a little RE prime in the other circuit, and we have the same setup, everything that went into finding a little RE prime. So it's still going to be 25 ohms in this example. But my little RL here is going to be 15 or 1.5K in parallel with 100K, or 100 ohms rather. Pull up my calculator and we'll whip that out. Let's see, there's going to be 600. No. Divided by 600. I get about 94 ohms, 93.75. We'll just call that 94. So my gain, just for the emitter follower by itself, is going to be little RL over little RL again, plus little RE prime. Now if you notice, I got RL on top and bottom, and in the bottom I'm adding little RE prime, so the bottom's always going to be bigger than the top. That means the gain of this one is always going to be less than 1. In this case, it's 94 over 94 plus 25. 25, I'm thinking ahead, it's going to be 119, so 94 over 119. Do that again, 94 divided by 119 gives me about 0.79 for my gain. So the emitter follower is actually going to take whatever voltage I put in here at the input and make it smaller. However, if I attach this to a common emitter amplifier, and it can be the regular one or the swamped one, either one. I grabbed the regular one here, it's okay. Now let's grab my emitter follower. Let's pretend I had 100 ohm load here. That means it's going to pull my gain of my common emitter way down. So what I do is I stick this emitter follower right there. We really don't need but one capacitor, but it'll be okay. This AC supply here, right in the middle, is that whole amplifier right there. And that load resistor we just covered up is whatever we see now looking into the front end of this amplifier. So what do we see looking into the front end of that amplifier? Well, I'll show you. We're going to see those two resistors, R1 and R2, in parallel. Remember, they got in parallel when we did the AC equivalent circuit. So we'll call this ZN. Let me get back to black here. Zn, the impedance looking into that amplifier, that emitter follower. We'll just use an I. Is going to be R1 in parallel with R2 in parallel with beta now remember, when I do resistors in parallel, my resistance, my combination resistance is always going to be smaller than the smallest one I started with. But here, this will be my smallest one because this is going to be around 90 something plus a 25. I think that was 119 we just saw a minute ago. So the whole emitter circuit here is 119 ohms. But it gets multiplied times beta. And if beta is 100, then that becomes 11.9 k ohms. And it's in parallel with the 25, and it's right here, and it's in parallel with the 4.4. So 4.4 now is going to be my smallest. So I've gone from having a load resistance for this common emitter amplifier of 100 up to something that's going to be in the neighborhood of 4.4K. So that's it. So even though this one has a gain of less than 1, that's going to increase the gain. Having that bigger load resistance is going to increase the gain of the common emitter amplifier to more than make up for it. I think that's a good place to stop for now. So again, I hope you're all doing well and come out of this virus quarantine okay. And we've got like, 3 days left. I do want to squeeze a little test in here, and I'm going to be sending back your old test from previous work in the next day or so. I'll be sending it by email, so I'm going to scan it and email it to you. Same thing with the next test I'm going to give. I think I'll put it in the email, and you can just work it on paper and photograph it and email it back to me like we've done some homework things. But we need to wrap all that up by Thursday because our exam is Friday. I didn't think to look at the time. Hang on a second. Before I started the podcast here, but I've got it. Yeah, Friday, May 1st from 2 to 4. Now, they want us to do it during the regular exam time. If you have a conflict, if you've got a job now and you can't do it during that time, I will work with you. You need to let me know what your conflict is and what times, hopefully that day, if possible, another time that day we could do it, because they're going to want me to turn in grades pretty quick after that. But if you can make it between 2 to 4 Friday, May the 1st, that's great. We'll do it online, and I'll be online answering questions as need be. And again, if not, let me know and we'll work out another time. Again, hopefully sometime Friday. All right. Have a good day.